The news keeps talking about urban heat island. I don't think this is a problem for just a few cities anymore. Sooner or later, every major city will have to deal with urban heat.
It is a design challenge, but every major challenge also creates an engineers who understand urban climate won't just solve problems, they'll be the ones clients turn to for advice.
When clients ask, how do we design for extreme heat? What will your answer be? We need science, we need simulation. Right now, I'm standing inside an Envi-met model of a real city. Here we can test areas, measure their impact, and understand how wind, material, and vegetation shape the urban climate. Here in this video, we will cover first. We will understand why cities are getting hotter and why this change is also a huge opportunity for architect, engineer, and urban planner. Second, I will show you one of my urban redesign projects where I use Envi-met to analyze the microclimates and test different design strategies. In that project, I made the outer space noticeably cooler during the summer without using a single watt of additional energy. It was surprisingly simple. You can do it too, so don't miss that part. Finally, we will talk about our future of our profession, the new opportunities that are emerging, and why urban climate design could become one of the most valuable skills of the next decade. Chapter 1. Understanding the enemy. Before we talk about solution, we need to understand the problem. Every summer, the headlines are filled with stories about heat wave. But heat wave and an urban heat island are not the same thing. A heat wave is caused by the weather. An urban heat island is created by the way we build our city. That's why two neighborhoods can experience the exact same weather, yet one of them can be several degrees hotter than the other. So what's happening? Many European cities were designed for a different climate. Were built to keep heat in, not heat out. Worked well for the cold winter, but the climate has changed. Today, these cities are facing conditions they were never designed for. At the same time, we've been replacing nature with concrete, asphalt, and stone. In nature, rainwater soaks into the ground where it nourishes vegetation and later cools the air through evaporation. But in many modern cities, water is quickly drained away. Instead of storing water, our city stores heat. Asphalt and concrete absorb enormous amount of solar energy throughout the day. Then, long after the sun has set, they slowly release that heat back into the streets. That's why some cities still feel unbearably hot at midnight. And materials are only part of the story. The shape of the city matters too. Tall buildings can block the wind, trap hot air inside narrow streets, and reduce the amount of heat that escapes into the night sky. Add fewer trees, darker surface traffic, and millions of air conditioners releasing heat back outdoors, and the city begins to create its own climate. The question is, can we redesign that climate? Chapter 2. Envi-met is one of the tools we can use to simulate and analyze the urban microclimate. In Envi-met, we can model buildings based on their height and geometry. We can also add streets, sidewalks, green space, ponds, different surface type, and a wide range of materials. Once the model is complete, we can extract different indicators, charts, and simulation results to identify problem and evaluate our design. Of course, generating the result is only part of the process. You also need to understand how to interpret different energy and thermal comfort indices. In this video, I'll briefly explain some of the most important indicators. If you'd like a separate video covering thermal comfort indices and international comfort standards in more detail, let me know in the comments. This project is from last year. It was a landscape redesign proposal for a 15 hectares residential community in Tehran. This is the master plan of the site. Here you can see the layout of the residential blocks and the public buildings, the green space, and the paved area. We had a highway along the southern edge of the site and relative busy main road on the western side. The pedestrian walkway were paved with concrete tile. The first thing we need to do is understand how shadows behave across the site. Typically, there is a one day of the year with the least amount of shade and another with the most. In the northern hemisphere, June 21st marks the summer solstice. It's the day when the sun is highest in the sky and shadows are at their shortest. On the other hand, December 21st is the winter solstice. This sun is much lower in the sky, creating the longest shadow of the year. Of course, the exact shadow patterns depend on your site location. That's why I always recommended analyzing both of the summer and winter solstice. Knowing where shade exists and where it's missing is one of the first steps in the climate responsive design. In Envi-met, you don't have to model every window or balcony. The overall geometry is what matters. Then you assign the right materials each surface. The software already includes detailed material properties and a large library of trees, so building the model is much easier. Now, I have to admit, Envi-met isn't the most visually impressive software, but that's perfectly fine. We are not using it to create beautiful rendering. We are using it to generate reliable data, chart, and environmental analysis. So, I modeled the site in Envi-met and ran the simulation. If you'd like to see how I built the model, let me know in the comments and I will make a separate video, a separate tutorial. You can run simulation for any day of the year, but if you are evaluating summer condition in northern hemisphere, I recommend choosing a few days after the summer solstice. By then, temperatures are usually close to their annual peaks. The sun is also slightly lower in the sky, making the effect of shading much easier to see. For this project, I choose July 1st. Then I extract the result at 3 different times of the day. The first was 6 a.m., shortly after sunrise. At this point, surfaces have released as much heat as they could during the night, giving us a good thermal baseline before solar heating begins. The second was 12 p.m., around midday, when solar radiation is rapidly increasing and outdoor conditions are approaching thermal stress. Finally, I analyzed the site at 7 p.m., just before sunset. By then, the surfaces had absorbed heat throughout the day and were close to their maximum temperature, allowing me to evaluate how much heat the urban environment retained by the end of the day. Now, let me show you some of the simulation results so you can get a better idea of how this process works. The first output is potential air temperature. As you can see, areas covered with asphalt consistently experience higher temperatures than the rest of the site. What's even more interesting is that these surfaces don't fully cool down overnight. Even at 6 a.m. after an entire night of cooling, they are still noticeably warmer than their surroundings. If there is one material that plays a major role in increasing airborne temperature, it's asphalt. You can also compare it with the unpaved area on the eastern side of the site. The temperature difference between bare soil and asphalt is quite significant. Envi-met allows us to extract many different environmental indicators, but one of my favorite is the PMV index. PMV, or predicted mean votes, is one of the most widely used indicators for evaluating human thermal comfort. It predicts how a large group of people would perceive the thermal environment on a 7-point scale, ranging from -3 meaning cold to +3 meaning hot. A value close to 0 represents thermal neutrality, which is generally considered the most comfortable condition. As a general rule, if most of your outdoor space remain within PMV range of -1 to +1, without relying on fossil fuel energy or mechanical cooling system, you have probably achieved a successful climate responsive design. In this project, the PMV results show that the site is relatively comfortable at 6 a.m. and conditions improve again around 7 p.m. But during the middle of the day, PMV rise well above +3, indicating severe thermal comfort. Then I compared the wind speed result with the air temperature map. That's when the main problem becomes obvious. The prevailing wind enters the site from the west. Unfortunately, the western edge of the site is also where we have the large paved areas, including the main parking lots. Throughout the day, the asphalt absorbs a huge amount of solar energy. As the wind passes over these hot surfaces, it picks up that heat and carries it into the residential area. So the first thing I did was relocate the parking areas. I moved a large portion of it between the residential buildings, where it would remain shaded for much of the day. I also relocate some parking area to the eastern side of the site. Why? Because if surfaces on the eastern side heat up, the prevailing wind won't carry that heat through the residential area. This is something I think is really important. Urban design should focus on simple, practical, and realistic solutions. It shouldn't be about adding trees anywhere, covering everything with grass, or proposing expensive material. The best solutions are often the ones that are easy to implement and make sense economically as well as environmentally. The second thing I did was remove 2 of the asphalt roads. Quite honestly, the site didn't need that much pavement. Even after removing those roads, the remaining street network still provides access to every residential blocks. As I mentioned earlier, asphalt is one of the biggest contributors to the urban heat island effect. The less unnecessary asphalt we have, the less heat the city stores during the day. Next, I replaced the green space where the western parking lots used to be. I also introduced a series of shallow water features along the western edge of the site. This area was simple. Since the prevailing wind enters the site from the west, I wanted it to pass through tree and water before reaching the residential area. This allowed the incoming air to cool naturally before it flows into the neighborhoods. This is what we call a cooling corridor. The strategy worked surprisingly well. It didn't just make the site look better, it also turned out to be one of the most effective changes in the entire project. One thing you should always consider in urban design is the prevailing wind direction. If you use it wisely, you can create something that behaves like a giant natural evaporative cooler. The simulation result confirmed exactly what we were hoping for. Cooler, fresher air was entering the neighborhood and flowing through the streets. I also placed a shallow water feature next to each parking area. As the wind blows across the water, evaporative cooling helped reduce the heat accumulated over the asphalt. As for the two asphalt roads that I removed, I replaced them with a bicycle path. Interestingly, the new bike lane now passes through the expanded green space on the western side of the site where the parking lot used to be. I don't want to make this video any longer. This project was just one example of how I approached the problem. I hope this project gave you a few practical ideas for cooling cities. But more importantly, I hope it changed the way you think about urban heat. Because sooner or later, designing cooler cities won't be optional. It will become necessary. Clients and municipalities will start asking the simple question: how can we make this place cooler? And they'll be looking for answer based by science, not guessing. That's where you can stand out. Learn the tools, understand the science, know how to test your ideas. I truly believe this will become one of the most valuable skills for architect and urban designer over the next decade. So if, like me, you think this field has a bright future, start learning today. Learn the right tool. Revit, Ladybug, and Honeybee are great for building performance analysis. Design Builder is excellent for energy simulation, and Envi-met is one of the best tools for urban microclimate analysis. If there is another software you think architects should know, let me know in the comments. Thanks for watching.